Okay, we're now at a point where you have gone through and practiced drawing visualization. We've talked about work holding strategies. We've talked about manufacturing processes, milling, drilling, boring, reaming, tapping. We've talked about different material types. We've talked about speeds and feeds to some extent. Now the final piece to operating, setting up, and involving yourself with production CNC would be those aspects related to writing NC programs. The understanding of an NC program lends an amount of power to you when you are setting up and operating. You're responsible for the piece that's being machined. You may not have written the part program, but it's still going to be incumbent on you to understand what that part program is doing so that you can avoid perhaps ruining some good, otherwise good pieces. Or if you are responsible for programming, that you want to apply the best practices when you create the NC program. So the next series of talking on my part will be to take you through the very basic concepts of G-code programming into some of the more advanced features, but not too terribly much beyond what you need to get started understanding and creating programs for some very basic components. And since we are now getting a bit machine specific, we talked about milling processes, we talked about turning processes, and other manufacturing processes. But now we're going to focus in and talk about milling, specifically programming milling machines. So up on the monitor here, I have a machining center. It's just a small picture, but it explains the table, the head going up and down. You've seen me demonstrate out on the shop floor the axes motions. You've seen us working the axes to indicate a vise in to make it true. So the concept of milling involves multiple axes. It involves our table moving from our left to right, which is generally our x-axis. It involves the table sliding in and out from you when you're standing right in front of it. That involves our y-axis. And then, of course, it involves the head of the machine and the tool going up and down, which is our z-axis. So the movements of the machine are a combination of all or one of the axes at any given time. Generally, milling applications, if you recall, taking an end mill, working it around the profile, involves simply dropping the Z to an appropriate depth and then moving our X and Y axes via these NC program codes we're going to talk about in a moment. But to understand NC programming, you need to understand and remember back to some of your basic mathematics courses or geometry courses. And if you recall something known as the Cartesian coordinate system. Cartesian coordinate system involves movement of axes. And they are identified as, if we were to look at a Cartesian coordinate system, we would have something that, like our table, moving back and forth in front of us along what we're going to call our x-axis. And then, taking the green marker, having the table move up and down involves movement of the y-axis. And lastly, if you recall, the head of the machine moving up and down involves an axis known as our z. So if you can picture now these axes, and we have some sort of table, which in our case you saw on the machine, the table had the slots for the vise. Table moves this way along the x-axis, moves that way along the y, and then the head of the machine moves up and down in the z. Incidentally, the Cartesian coordinate system was named after a person known as René Descartes. He was a French mathematician, philosopher, and he rationalized this concept of a coordinate mesh in the 3 dimensions of our world: our length, our width, our height. So we can think of the Cartesian coordinate system as a series of potential points existing in space. So let's for the moment just picture a 2-dimensional movement of our machine. Let's just imagine our head looking down on the table, and the table moving from left to right and up and down. It's going to be a 2-axis view of the table. So what I'll do is take the Cartesian coordinates that I've drawn up, and I'll only draw them up as x and y axes at this time. So here I have an axis of motion that we're going to call x. So imagine this as our table going up, back and forth. And now we also have an axis of motion that we will call y, which represents the table moving. Again, we're looking straight down, our nose is in the z, and the table's moving up and down, left and right, x and y. Now, the concept of a Cartesian coordinate system is that points that exist in this coordinate system can be mapped in terms of units. So a point might exist in 1 inch over in x and 5 inches up in y, and so on. All points in the Cartesian coordinate system can be mapped in terms of x location, y location, and z location. So where do those numbers come from? Well, where our Cartesian coordinate axes intersect, where the x and y intersects, that is said to be our datum location. That is the origin of all coordinates. It is termed as 0 in the x and 0 in the y. So it's an x value and a y value. This exact point where these 2 systems cross, these 2 axes cross, are the origin of all coordinates. And they are termed as 0, 0. Now, if we were to say, okay, I have a part that exists in space, and my part has 4 corners. That part is defined in terms of 4 points. But before I get into these segments of points, etc., what I'd like to do is just think in terms right now of 2-dimensional points. Just series of x and y values, point values. So our coordinate system is origined where they intersect. And we then take each axis and divide it up into units. Again, these units might be inches, they might be millimeters. Let's not concern ourselves with the unit values at this point, other than they're equally spaced along the axes. So this might be unit number 1, unit number 2, unit number 3, unit number 4, 5, and so on. And likewise, going up in this direction, this might be unit number 1, 2, 3, 4, and 5, and so on. Now, we're not looking at this in terms of the z dimension right now, just in terms of x and y. And then, likewise, to the left of the origin is 1 unit, 2 units, 3 units, 4, 5, and so on. And likewise, below is 1 unit, 2 units, 3, 4, 5, and so on. So we now can sit and look at these grid locations. And if we simply, in our mind, now project a grid like grid paper over these points, so here's our grid locations in x, and here's our grid locations in the y-axis. Can you see what's happening now? Grids have intersections. Now, if we say, all right, I have a point, and it lives right here. This point is 4 units out in x, and 5 units up in y. This point is said to be located at x of 4 units, and y of 5 units. I just arbitrarily picked that intersection point right now. Again, the grids can be spaced in terms of inches or millimeters or fractions of an inch. At this point, it's important to simply know that there's some kind of unit on the axes, and these units exist in all 4 of what we're going to call quadrants. And this is also an important concept, this notion of quadrants. So, we have an origin point right here that is said to be 0, 0. Anything going in this direction, to the right of 0, 0, is said to be in the x plus. Any of these grid locations to the left of our origin are said to be x minus. So this is x minus 1, x minus 2, x minus 3, 4, and minus 5. Now likewise with our y. Anything above the x-axis is said to be y plus. Anything below is said to be y minus. So this is minus 1, minus 2, minus 3, minus 4, and minus 5. So we can now position a part anywhere on this grid for our consideration. So if you look up here, we have the table, the head, and really our NC programming is just an exercise, believe it or not. You can boil it down to as simple as thinking of it as a series of connect the dots. And that's all it is. Let's go on and expand on that a little bit. If you look at this grid from your workbook, you'll see the thick dark lines represent the axes of x and the axes of y. We don't have the z shown at this point. But here are those quadrants that we're talking about. Here's our origin point. It's 0, 0. So everything up to the left and above exists in what we call the x plus and y plus quadrant. This then is the x minus and y plus quadrant. This is the x minus, y minus quadrant. This is the x plus and y minus quadrant, which means that any x value here is going to be a plus, any y value will be minus. Why is it minus? Because it's below the x-axis. And here are some samples of points rather, that exist on a grid. These are just units again. Think of them in units right now. Don't worry if they're inches or millimeters or anything like that. It's just that we have various units, and you can think of them as inches if you like. But if we now look at the dots, And let's do this together. Dot number 1 is located right here. Based on our gauge, where is that? In the x minus y plus quadrant. So if I were to ask you, please identify to me where point 1 is in space, you would reply by saying, okay, point 1 exists at x minus 10 units, so x minus 10, and y plus 5 units. Number 1 is said to exist at x minus 10. How do I know that? Because this point is 10 grid points to the left of the origin. Point number 2 exists in the x minus y plus quadrant, so it exists at x minus 7 and y plus 2. Point number 3, is that in x plus or x minus? It's exactly at x0, if you'll notice. And where is it in y? It's 5 locations up in y. So point number 3 is said to exist at x0. In other words, it lies right on the origin in the x-axis, but it's above in y plus 5. So point 3 is said to exist at x0 and y plus 5. Take a minute, think about the rest, and then we'll go over them. Okay. Point number 4 is located right here. That's in the x plus y plus, so point number 4 is at x3, y2. Point number 5 is in the x minus y minus, so it is at minus 1 unit in x and minus 1 unit in y. Point 6, it exists at minus 8 in x, minus 7 in y. Point 7 exists in x plus 6, y minus 5. Point 8 exists at x12, and he's right on the y0, so x12, y0. Point number 9 is at x positive 9 and y positive 5. So that's really what underlies all of the x, y, and z coordinates in a NC Park program that you may have seen. Everything exists somewhere in the Cartesian coordinate system. And you also can think of your machine. If you remember, we were traveling our table to as far to the right as we could move it, and then as far to the left as we could move it. Our table has travel limits, so we can say that from the center, our table might be able to move 20 inches in x all the way to minus 20 in y. So it would be said to have 40 inches of travel. And then likewise in the y-axis, it might be able to move from y10 to y minus 10. So it's said to have potentially 20 inches of travel. Or the table travel might be centered right here and sit off to the right. So the machines might have sit like this, which means that we'll go from x0 to x40 and from y0 to y minus 20, for example. But everything exists on the Cartesian coordinate system. So here is an exercise I would like you to try, and in a few moments we will work on this together. Look at the Cartesian coordinate system centered on this part outline. These represent the object outlines of a part. Let's call this point number 1. And notice the direction arrows. So this here becomes point number 2. This is point number 3, number 4, number 5, number 6, number 7, number 8, number 9, number 10, and number 11 is also point number 1. So please fill in the coordinates in terms of x and y for all of these points.